Welcome to the art and science of Mead, all about acids and pH. In today's presentation, we will discuss the types of acids which are found in honey and in mead. We'll review the difference between pH, titratable acidity, total acidity, and volatile acidity. I'll discuss why it is important to measure and adjust pH and TA, and I'll also review the methods of measuring pH and titratable acidity. Finally, I'll talk about how to adjust pH and titratable acidity, including tasting trials, acid additions, and deacidification. What are the types of acids found in honey and in mead? There's many types of acids that are found in mead or added to mead later, either as an acid addition or as a fruit. The primary acid found in honey is gluconic acid, but there's other types that we find from fruit, including tartaric acid, malic acid, citric acid. There's some other acids as well, including succinic acid. And then there's ascorbic acid or vitamin C, which we sometimes use for antioxidant purposes, or sorbic acid, potassium sorbate, which we add to prevent re-fermentation in the bottle in a sweet mead. There are also some acids that are undesirable, including acetic acid, which is the same acid in vinegar, lactic acid, unless we're purposely making a sour mead. Lactic acid is something that we typically do not want. And then finally there's butyric acid produced by spoilage organisms. There's actually many other types of acids found in mead and in honey, but these are the primary ones. So gluconic acid is the primary acid found in honey, and it's produced naturally through the action of the enzyme glucose oxidase on glucose, which is in the honey itself. What is interesting about gluconic acid is that it exists in balance between it and its lactone, gluconolactone. This hydrolysis reaction is important because it can affect the accuracy of how we measure titratable acidity in mead. And I'll talk about this much more in another separate presentation. This phenomenon is called the falling endpoint or fading endpoint when we're attempting to measure acidity in honey or in mead through acid-base titration. But I'll talk about that more in another presentation. Gluconic acid is considered to be one of the weaker acids. It's only mildly sour compared to the more sour acids such as tartaric or malic acid. The gluconolactone itself actually isn't sour at all. It's more of a sweet or bitter flavor. And the relative sourness of gluconic acid is maybe only about 1/3 that of citric or lactic acids, and only about 1/4 as sour as acetic, malic, or tartaric acids. So the acids that are in mead which come from fruit can come from fruit itself or fruit juice. One of the primary ones we use is tartaric acid, which is found primarily in grapes, but also in some other fruits as well, including tamarinds. It's the most important acid in grape wines, but it does not occur naturally in mead unless it's added using grapes, grape juice, or as an acid addition. One of the things that's unique about tartaric acid is, unlike malic acid, it does not get degraded by microbial activity. It is more effective than malic acid at lowering pH. More of a problem in wine is that you can have those crystals. If you've ever poured a wine and found crystals at the bottom of the bottle, that's from the potassium bitartrate crystals. You know, all these acids are sour, but they've been described by different people in different ways, but tartaric acid is considered to be a strong and sour acid. Malic acid, that's the acid that's found in apples and also many other fruits, including berries. It's important because it can add a lingering tart green apple-like flavor, which may or may not be desirable. It can be metabolized by both bacteria and some strains of yeast. Winemakers will use specific strains of lactic acid bacteria to soften the sourness of malic acid by converting it to lactic acid. We don't use malolactic fermentation very much in mead. I've used it in some pie mints and some melomels, but it's not something that we would normally use, say, in a traditional mead or a mead that does not contain malic acid. And then finally there's citric acid, which comes from citrus fruits. It also can be metabolized by microorganisms. That's one of the reasons why I don't recommend it as an acid addition, because it can be converted to acetic acid or even diacetyl. You can use it after fermentation and you would not have that problem. But one of the downsides of citric acid is it's a very tart, almost a sour, puckery, sweet tart type of flavor. Usually it doesn't seem that it belongs in most mead, except perhaps if you're making a citrus fruit mead, then of course that would be the preferred acid that you might consider adding. Another acid is succinic acid, and this does not occur in mead naturally, or I should say honey naturally, but it occurs as a product of yeast fermentation. So even though it does not exist in the honey, it develops in mead through the process of yeast fermentation. And it's been described in different ways, including being salty and bitter. There can be increased succinic acid production with certain strains of yeast if there's higher pH, high sugar must, anything that's stressful, such as high fermentation temperatures, too many nutrients, or too much aeration. It forms an ester, monoethyl succinate, which can result in a mild, pleasant fruity aroma. And the development of the succinic acid during fermentation is one of the reasons why you'll see your pH drop slightly as fermentation begins. Other acids, formic acid. Doesn't occur in a very large amount, but it's interesting because it does occur in honey naturally. It's produced by Hymenoptera, bees, ants, wasps, and beekeepers. If you're a beekeeper, you know what this is because it's one of the treatments that we use to treat varroa mites. And it's very pungent if you've ever smelled it. And if you don't know what this smells like, if you go outside to an anthill and you pick up an ant between your fingers and then you smell that ant, often it'll release formic acid, and then you'll know exactly what formic acid smells like. Ascorbic acid, or vitamin C, we add as a natural antioxidant. It's used to prevent oxidation at time of bottling, or sometimes we use ascorbic acid when we're trying to manage some of the sulfide flaws, specifically dimethyl sulfide. It has a light sour flavor. Sorbic acid is used as an antifungal, and it basically is used to stabilize mead, which has residual sugar. One of the downsides is if there's any malolactic bacteria present, it can be metabolized into 2-ethoxyhexathreefive-diene, which has a geranium leaf type of aroma. It's called geranium taint. So you never want to use sorbic acid in a mead that you're planning, or there's a chance of there being malolactic fermentation. I'm not going to talk about the ascorbic acid and sorbic acid very much. I've discussed those more in other presentations, but I'm just mentioning them here. So some of the undesirable acids that can occur in mead: acetic acid, which is the same acid in vinegar, and it can be produced by certain bacteria, including Acidobacter or Gluconibacter, but you do not have to have the bacterial infection for that to happen. It can also be produced by yeast, especially under stressful fermentation circumstances such as high temperature. The acetic acid is the acid of vinegar, so that's what it smells and tastes like, although at lower amounts it might have more of a bitterness. There is lactic acid, which is produced by lactobacillus and other bacteria. It's like yogurt or sour milk. It's not quite as tart as some other types of acid, which is why it's encouraged to form on purpose via malolactic fermentation to decrease the tartness from malic acid. We typically don't do that in a traditional mead, but in somebody making a pie mint that's more of a wine style, that might be something that could be considered. And it really, whether it's undesirable or not, it depends what you're doing. Of course, if you're making a sour mead on purpose, you want lactic acid, you're trying to do that on purpose. But when you're not intending that, then it's considered a flaw. And then finally, there's butyric acid, which is produced by spoilage bacteria, and it's basically like stinky, rancid, rotten cheese. So obviously not something that you'd want to have in your mead. Here's just a chart showing a comparison of the different types of acids and some of the flavor that some of the other authors have described between the different types of acids. And obviously those are subjective. I recommend you make up a solution of each of these and taste them for yourself so that you can have a better understanding of what they taste like and what their flavor is like. This is a publication from Steinkraus and Morse. It's an older publication. It's from 1973. And basically it's showing that the total acidity of mead, it can be quite variable depending on the base ingredient, the honey specifically, anywhere from 2.2 up to just over 7 grams per liter. That's a huge variation, and that's why it's important to remember that when you're thinking about acid additions, you really should not do it by measurement, so many grams per liter or so many teaspoons per gallon or anything like that, but rather you should determine how much acid you need to add, if you need to add any acid at all, based on taste. And the best way to do that is through tasting trials, which I'll cover a little bit later in this presentation. This is a Polish study, so obviously this is Polish mead. You can see the different dilutions, 1 to 3 versus 1 to 2. They decided to call it wort. This was a translation from a Polish study, so they really should have used the word must. But anyway, it's showing you how over time there's an increase in the total acidity, even within just 4 to 7 days, and most of that increase is actually from the succinic acid that we had mentioned. There's a slight and slower increase in volatile acidity that occurs over time as well. Here's another chart from that study looking at the concentration of various acids. They did include formic acid here, which you can see occurs at very low amounts, and it doesn't change at all. Acetic acid or volatile acidity does increase over time, as does succinic acid. And succinic acid increases to its maximum usually around 7 to 10 days, and by then active fermentation is done, and then it remains fairly stable. pH, titratable acidity, total acidity, and volatile acidity. What's the difference? Some mead makers get confused about the differences between the different types of acids or ways of measuring acids or pH. pH basically is a measurement that's related to the concentration of the free hydrogen ions in the solution. By definition, it's the negative log of the free hydrogen ions. The pH in fruit juice can range from being as low as a pH of 2 in lemon juice up to 4 for warm climate grapes that tend to have lower acidity. Honey has an average pH of around 3.9, but again the range is rather large, between 3.4 and 6.1. And the thing to keep in mind is for every 1 point change in pH, the amount of acidity increases tenfold. So if you go from a pH of 4 down to a pH of 3, the acidity has increased by tenfold, but then if you go down to 2, so a pH of 4 down to a pH of 2, the acidity is increased by 100-fold, 10 times 10. So it increases or decreases logarithmically as you go up and down the scale. Hydrogen ions are produced from the dissociation from the acids in solution, and so we're measuring the hydrogen ions when we measure pH. So where the pH measures the concentration of the free hydrogen ions, the titratable acidity measures the total amount of hydrogen ions, both the free hydrogen ions that are disassociated, and then the undissociated hydrogen ions, as neutralized by a base, typically sodium hydroxide, that we've titrated. The thing that's important, though, these are different measures of acidity, but even though they're related, they're not necessarily in a linear fashion. It's not a predictable relationship. Rarely you can have a mead or a wine that has a relatively high pH and also a high titratable acidity. We often see this in melamels that are high in malic acid. So even though there is certainly a relationship, you add acid, typically the pH will go down. It's not predictable or linear, and it's an important concept to keep in mind. So titratable acidity We often use that interchangeable with total acidity, but they're not really the same thing. Titratable acidity in the United States is reported as grams per liter of tartaric acid, as has been measured by titrating with a base up to an endpoint of 8.2. Now, sometimes it's reported rather than grams per liter, more of a percent, grams per 100 liter, and so that's reported as a percent. This can get confusing, but it's really very easy to correct for. You just multiply, if you see it as a percent, just multiply it by 10 to move the decimal point over by one spot, and then you'll get the titratable acidity in grams per liter. Now, in some countries, they titrate to an endpoint of 8.0 or 8.3, but these are close enough as to be considered interchangeable and to be equivalent. In some countries, they report the titratable acidity not as grams of tartaric acid, but rather grams of sulfuric acid. If you're reading the wine literature and you see that, it's easy to convert by just multiplying the grams per liter of sulfuric acid by 1.5 to get the measurement in tartaric acid equivalents. So total versus titratable acidity. These terms have been often used interchangeably, and myself, I've done it as well until I learned more about this. And although they are related, they are not exactly the same thing. And this is important because later in another presentation, when I talk about falling endpoint or fading endpoint phenomenon, when I talk about measuring titratable acidity, it's important to understand these are different. Even though they're closely related, they're not the same thing. So titratable acidity is a measurement of the acids in a solution which can be titrated with a strong base. It's a measure of the total available hydrogen ions in solution. The total acidity, on the other hand, is a measure of all of the acids which are present. So it's a measure of both the dissociated and the undissociated forms of each individual acid. So that is why the titratable acidity will always be slightly less than the total acidity. Another acid is volatile acidity. So most acids in wine or mead are fixed, that is, they're non-volatile. They don't evaporate when being heated, but some acids can evaporate when heated, and that's called volatile acidity, or VA for short. And most of us think of it being acetic acid and ethyl acetate. However, formic acid actually is included in that, but it occurs in such small amounts in honey and in mead that it's such that it's not really considered to be a significant part of volatile acidity. If you're a commercial mead maker, you need to be aware there is a legal upper limit that's permitted in wine and mead. The red wine 1.4 grams per liter, white and dessert wines 1.2 grams per liter. High volatile acidity is considered a flaw, so think of vinegar and think of nail polish remover. A very low amount might be tolerable, but if you have too much of it, it can be a mead flaw. So, pH, titratable acidity, total acidity. Are you confused yet? Well, this next slide, I'm going to try to make it as clear as I can for you so that you can understand the differences between these measures of acidity. So you have the different acids here. The purple T is tartaric acid, the green M is malic acid, and the yellow C is citric acid. You see the hydrogen ions that are attached to those acids, those are non-dissociated hydrogen ions. And then you see the orange hydrogen ions that are floating free, those are what we consider to be dissociated ions. So when you add an acid to a solution, some of the hydrogen ions will dissociate and become free hydrogen ions. And those are what the pH is a measure of, the negative log of those free hydrogen ions. The titratable acidity is a measure of the hydrogen ions that are both dissociated, floating free, not attached to an acid, as well as the ones that are still associated with an acid. So both the white hydrogen ion and then those orange ones. So it's the measure of all of the hydrogen ions. Total acidity, on the other hand, is not a measure of the hydrogen ions, but of the acids themselves, of all of the acids in the solution. And so that's the difference between pH, titratable acidity, and total acidity. So why measure and adjust pH and acidity? Acids have two main purposes in mead. For one, it's important to have a sufficient amount of acid, but not too much, to keep the pH within the desirable range so that healthy fermentation can take place. For microbial stability, higher pH will be a more positive, an environment that would be more friendly to unwanted microbial activity, and also to maintain optimal sulfite levels. The lower the pH, the more effective the sulfite is. I talk about this much more in my sulfite talk. Acids are also important for organoleptic benefits. A higher acid will minimize oxidation. It helps provide balance against any residual sugar. It reduces the perception of sweetness. And the higher the acid, lower the pH, the better the color retention. So what's a desirable pH range? Again, I want to stress this range is a sort of more of a rough range. You can be slightly outside of this and still be okay. Too low of a pH during alcoholic fermentation can cause yeast stress. So we try to keep the pH from being too low or less than 3.0. That said, yeast is very forgiving. I've had batches that were down to 2.8 and they did fine. But it's not something that I would recommend allowing to happen. And that's why if you're planning on making a mead that's going to use citrus fruit or citrus juice, something that's highly acidic, it might be better to do the primary alcoholic fermentation first and then add the citrus juice or the citrus fruit after the alcoholic fermentation is over. So that way you can avoid dropping the pH too low and stressing the yeast during the fermentation itself. You also don't want the pH to be too high because high pH, particularly over 3.9, can encourage other microorganisms, spoilage organisms, to occur later on. So other benefits of monitoring and adjusting acidity and pH. I already mentioned spoilage organisms are inhibited at lower pH, so you want to avoid high pH. It's important for the appearance, so especially red piments and melomels. Those with a lower pH will have more purple and ruby tones, where those with a high pH will have more brick and orange tones. It's important to keep the pH within the desired range because higher pH increases the rate of oxidation. Lower pH tends to result in a more rapid precipitation of unstable proteins. And that's important because this also can affect the effectiveness of fining agents. I thought I made this amazing discovery myself. I found that if I added a fining agent, not much would happen, but then if I did an acid addition shortly afterwards, magically, almost overnight, the mead became clear. It turns out this is something already well known in the wine literature. Certain fining agents are more effective at lower pH, and I discussed that in much more detail in my fining agent presentation. pH also increases the effectiveness of sulfites. If the pH is higher, you'll have to use much more sulfite. You'll have to have a much higher free sulfite range to have the molecular sulfite that you're aiming for. The pH and acidity also affects the balance and the perception of sweetness. So when we think of balance, we think of two sides, and this is a little oversimplified, but basically sweetness from sugar and alcohol are one side of the equation, and on the other side we have acid, tannin, and carbonation. And so if you have a sweet or semi-sweet mead, it might seem out of balance, it might seem syrupy or cloying, and you could balance that by adding acid or maybe tannin, or you might decide to carbonate it. All of those things can help reduce the perception of sweetness and make it seem more in balance. Obviously what you would not want to do is add a lot of tannin, add a lot of acid, and then carbonate the heck out of it, because then it would seem harsh. And so this is something that it's easy to show someone, here, taste this in this glass. Does it seem in balance or not? It's easy to show someone, but it's more difficult to explain. There isn't really a measure. There's not like an equation or a formula you can use that can tell you, how much acid is what you need. You have to figure this out yourself by tasting trials. Now, in the wine literature, and I didn't provide references because these were taken off of the internet from various sources, but in the winemaking, they do have targets for titratable acidity depending on the style of wine and how much residual sweetness is left. One thing I've noticed though is if you try to use these targets in mead, they don't always work out so well. And so whatever recommended ranges for titratable acidity in wine you might use, they don't always translate directly to mead. And that's why it's very important to learn how to balance acid and to Determine your acid additions not by trying to aim for a certain number or a certain range, but rather to do it by taste. How do you measure pH and TA? One of the most important pieces of equipment after, say, a hydrometer is a pH meter. We can use them both for measuring the pH as well as the titratable acidity. I would not use pH strips as they are not accurate enough to measure for wine or mead making purposes. At the minimum, you want a pH meter that can measure down to 0.01 pH. And usually we calibrate with two different solutions, 4 and 7. You need to care for the electrode so that it can have a longer life, so you need to clean it and store it properly. Basically what the pH meter is doing is it's measuring the change in the electronic voltage potential of the solution being tested. So the electrode, which we sometimes call a probe, has an electrolyte solution within it which responds to the hydrogen ions within that solution. The preferred tip shape of a pH electrode is spherical, and if you're buying one of these from a wine supply company, you know you're going to have the correct kind, because they're obviously not going to be offering a pH monitor that's designed, or meter that's designed for some other solution. You need to be really careful. So this one I ended up dropping down into a glass jar, and it just shattered, and that's like a $200 mistake right there. So they are glass and they can break, so be very careful with them. Some pH meters have ATC, automatic temperature compensation. The measurement of pH will be affected by the temperature of the solution slightly, and so if you have ATC, it will automatically compensate for that. Some of the higher end probes will also have a refillable electrolyte solution and anti-clogging technology. There are single junction and double junction models available. If you're buying one of the more cheaper versions, that's fine. But it's more likely to be a single junction, of course, and more likely to be contaminated and fail. Whereas double junction is more expensive, but it's less likely to have any problems. One of the important process is when using a pH meter is you need to calibrate it. If you're getting any unusual values or values that don't make any sense, the first thing I do is I clean it and then I calibrate it. If you're going to use it all day long, it's probably best to calibrate it every 4 hours. And usually we do two-point calibration with standardized buffer solutions, typically 4.01 and a pH of 7.01. There are some models that actually allow 3-point calibration testing. Cleaning. So it needs to be kept clean and stored properly. So between use, I rinse with distilled water, and then periodically we clean the electrode with commercially available cleaning solutions. It's very important to know not to clean or try to dry your probe with a cloth or a paper towel, as you could damage the membrane. So try not to touch the membrane with anything other than the solution you're testing the pH with, rinsing with distilled water, the pH buffer, of course, when calibrating, and then any of the commercially available cleaning solutions. It's important to store these correctly too, as per the manufacturer's recommended recommendations. If you're not using regularly, you change the storage solution every several weeks. If you find you've run out of storage solution, you can temporarily store it in one of the buffers, but only temporarily. But do not store it in distilled water, and try not to ever let it dry out. If it does dry out, let's say you found it and you forgot to refill the storage solution, that's fine. You can just store it in the storage solution for a few hours, and usually everything will be fine and it'll work just fine after you do that. Troubleshooting. The meter will not turn on. Well, obviously, first check the batteries. If there's a switch, make sure to check that. But if none of those things help, then maybe the meter's broken. The meter will not calibrate. Well, first make sure your buffer solutions are fresh. They don't last forever, usually maybe up to 6 months after opening. If it's a brand new meter, you might need to soak it longer in the solution to finish conditioning, or perhaps the meter is broken. If it's a meter that will no longer calibrate, it's possible your electrolyte has simply gotten old and needs to be replaced. They do not last forever. So if the pH reading is drifting, either you need a new electrode or maybe it just needs to be cleaned. This is when you're testing a pH of a solution and it just doesn't seem to hold it. You're trying to get the reading and it seems to be drifting, up or down, and it's not really getting you a solid reading to be able to record. And then a related problem is if it takes too long to stabilize. So maybe the membrane's clogged, maybe it needs to be cleaned. So use the recommended cleaning solution to see if that helps. So measuring titratable acidity by endpoint titration. What is it? Basically, a strong base, sodium hydroxide of a known concentration, is slowly titrated into a weak acid. In our case, it would be mead or juice or wine. And as you titrate, you watch the pH. And when you get to the predefined endpoint, in our case, it's going to be a pH of 8.2. That's when you record the volume of sodium hydroxide that you used. And you can use that volume to calculate your titratable acidity. So the equipment to do a endpoint titration is you need a calibrated pH meter, a burette clamp, and a stand. You need a beaker, a standardized solution of a sodium hydroxide. Usually we use 0.1 or 0.133. It doesn't matter as long as you know what it is, so you can use that in your calculation. And then a stir bar and a magnetic stir plate, because as you titrate in, you want it to be stirring quickly so that it mixes well and you get an accurate endpoint. And there's my setup. It's my vinimetrica. I also use a Hanna now, but this is my vinimetrica that I've used for years. It's a great apparatus, and I think it's one step up from starting with just a simple pH meter, but I think it's a really good value. So Tom's tips for titrating. So first, make sure your sample is at room temperature and does not have much carbonation in it. Remember, if it's carbonated, there will be some carbonic acid, which could affect your endpoint reading. So if necessary, you need to degas it. Either leave it out or just put it with the stir plate running for a little while until all of the CO2 comes out of the sample. Take a measurement of the pH. Record the volume of the sample in milliliters, so how much are you going to titrate into, because that's important for your formula. And you basically titrate each sample with the sodium hydroxide solution, drop by drop, up to an endpoint of 8.2. And it's important you do this fairly quickly, but not too quickly, because you don't want to overshoot that endpoint. So starting out, this would be a little bit too slow. It would take you forever to get there. If you are titrating so quickly that the drops all flow together to where you can't distinguish them, that's too fast. So you want to go fairly quickly until the pH gets to around 6.0 or so. So maybe a drop per second or a little faster than that. And then once you get to a pH of 6.0, remember there's that inflection point, and it will rather rapidly shoot up to, from a pH of 7 up to over 8. So you want to slow down towards the end, and maybe even slower than this at the very end, because that way you won't overshoot the endpoint accidentally. And then you finally read the burette, and record the volume in milliliters of how much sodium hydroxide you used to reach that endpoint. And there is a formula to calculate this for those of you that are interested. This is how you calculate it. Myself, I'm lazy. I just use a winemaking app or one of the online calculators, and I just add in these numbers to that calculator, and then it tells me exactly what the titratable acidity was. So troubleshooting. Sometimes the concentration of our sodium hydroxide is simply wrong, so it's important to standardize the solution. I didn't include that in this presentation, but you can definitely look it up how to do that. I purchased a solution a little while back, and it turned out rather than being a 0.1, it was a 0.01. And obviously, as I was titrating, it was taking forever, and I realized something was wrong immediately. So I went back and standardized it, and it's like, oops, even though the bottle said 0.1, it was actually like not even close to that. So even if you're getting this from a winery supplier, just be aware they can make mistakes too. So it's always wise to standardize a solution, and then over time, some of these solutions can lose strength. So you might want to be paying attention to that too. The incorrect volume of the sample. So if you pipetting too quickly, you might put in a few extra drops, and it can give you an error. So you want to titrate relatively quickly, but not too quickly. Otherwise, you may overshoot your endpoint. Carbon dioxide in the sample, I already mentioned, if there's dissolved CO2, it can make the titratable acidity to appear higher. So it's important to degas a sample if there's any carbonation present. If the sample is not fully clarified, there can be some compounds present that can interfere with the titration slightly. An old solution. So always use a fresh solution. They usually recommend tossing it out after 6 months. If you're unsure, standardize it. Again, you can look that up. There are resources online for how to standardize your solution. And then, incorrect reading of the endpoint. So, titrate and read it carefully. Obviously, if you're not paying attention or you record the wrong volume, that's going to add error to your calculation as well. Well, I'm not going to go into this too much other than to show you there is a way, if you're very lab-oriented, to measure volatile acidity through a cache still. I think these apparatuses are very cool looking in a mad science sort of way. But basically, you're going to try to measure the acidity after you've heated it, and that the difference between that and the endpoint width is going to be the volatile acidity. Most of us, or if you're a commercial meter, you're probably just, if you really want to know the volatile acidity, it's probably just a lot easier to send it off to a commercial winery lab to get that measurement for you. But if you're interested, there is a way to do this in your own lab. And again, I think the labware is really cool looking. But yeah, so that's enough about volatile acidity. Acid adjustment, acid additions, and lowering acid levels through deacidification. How to adjust the pH. So increasing the pH can be done by adding either potassium carbonate or calcium carbonate. There is a level of how much you can add. If you add too much, you might cause there to be a chalky taste, so be aware of that. Lowering pH is a lot easier. You simply add acid. My preferred acid addition is tartaric acid, although I'll use malic acid too, especially if it's, say, a sizer that normally has malic acid in it. Or you can just add high acid citrus or fruit juice to lower the pH. I tend to avoid citric acid or acid blends with citric acid, especially pre-fermentation, because of the chance of increasing volatile acidity, acetic acid, and also the possibility of a diacetyl, which you might not want. Afterwards, it's not so much of a problem, but again, the citric acid has this sour, puckery, sweet tart type of flavor, which is something you might not want unless you're making a mead that does naturally have citric acid in it, such as one made with citrus fruits. So too much acid. There are certain strains of yeast that will metabolize malic acid into ethanol. This is not the same as MLF. This is not malolactic fermentation because lactic acid isn't being produced. Malolactic fermentation is done by certain strains of bacteria, not yeast. But there are yeast strains that will decrease malic acid slightly. The most common one that we know about and use is 7,1-B1122, but Lauvelin C actually even has a higher reduction of malic acid than does 7,1-B. There are some non-Saccharomyces species of yeast which can be used to metabolize malic acid, sometimes reduce it by as much as 80 to 90% or more. An example of this is Schizosaccharomyces pombe, but it's not available commercially. I've looked for a source and I really couldn't find it. I'm sure I could find it if I looked a little bit harder. But I've had good success using these yeasts in batches where I knew the malic acid level would be too high, just to decrease it slightly through fermentation. Malolactic fermentation, on the other hand, that's through certain species of bacteria. We do not tend to use it in mead very often. I've used it myself. I've had mixed results. Sometimes I've been pleased, and sometimes it didn't do exactly what I wanted it to do, and other times I was kind of neutral about it. But a place where you might use it would be, if it's a wine style of mead like a Pyment or maybe some berry melamals, you can use the malolactic fermentation with these bacteria. Be aware, though, it might result in some effects you don't want, like excessive volatile acidity or diacetyl. And then some strains produce biogenic amines, which that might actually be the cause of wine headaches. So when people say they get red wine headaches from sulfites, we know that that's not true. Sulfites are not the cause of wine headaches, but people certainly do get wine headaches from certain wines, and red wines in particular, and it might be the biogenic amines that occur as a result of malolactic fermentation. Well, what if there's still too much, and you've tried those other things, or it just happened, so you have a few options. One is to try back sweetening to soften and balance those acids. That can work very well, but you need to be careful. There's only, back sweetening can only go so far. If it's extremely sour, extremely tart, and you try to back sweeten your way out of it, you're going to now have a sweet and sour, or a sweet and tart mead, which is going to be, I call it, twice out of balance. So it'll be too sweet and too tart, and it's not necessarily going to be improved by this. So if you have something like that, it's probably really wise to do tasting trials to see, am I going to be able to get myself out of this situation by back sweetening alone, or do I need to think about doing other things? Another option, if it's too acidic, is just simply save it and use for blending with other batches of mead that are excessively sweet. You can use it as your acid addition, or you could consider deacidification. If you only need to lower it by 2 or 3 grams per liter, then you can use any potassium bicarbonate, potassium carbonate, calcium carbonate to lower it slightly. But if you need to remove more than that, you have to be careful. For one, you can add flavors you don't want. I mean, think chalk. And then it can also be hard to reduce it. So in that situation, you need to use a technique called double salt deacidification method. And the way that works is, if you're trying to reduce acidity with potassium bicarbonate only, potassium malate, which is from malic acid, is relatively soluble and it's very difficult to remove, unlike potassium tartrate. So in this method, you use calcium carbonate together with this, because if you try to use calcium carbonate alone, you're going to remove most of the tartaric acid before you reduce any malic acid. So what you do is you remove a portion from your batch, around 20 to 40% of the volume. You add enough calcium carbonate to the portion you remove to get the pH high enough, at around 4.5. So when the pH is that high, both calcium tartrate and calcium malate will form. And then what you do is you add that pre-treated portion with the calcium carbonate back to your main batch, and you mix well. And after several hours, you test the titratable acidity and the pH. And that's very important because you don't want to overshoot. Obviously, you do not want the pH to be too high, because that can cause problems. So in order to avoid errors with this method, I strongly encourage you to use a spreadsheet or an online calculator to make sure you calculate correctly. And it's really important to perform bench trials first, because if you don't, and you do this and you make a mistake, you could theoretically ruin your whole batch. And so try not to remove too much acidity. Some acidity is needed for organoleptic reasons, and also to keep the pH. And if you raise the pH by too much, I guess you could add some acid back to compensate for that. But it's always better to perform bench trials first and make your calculations accurately before you actually do something like this. I consider this to be a sort of a last-ditch effort. It's not something I'd recommend as a first or even second line approach to excessive acidity, but it is something to keep in mind and keep it in your arsenal if their day comes when you actually have to try this. So determining how much acid to add, pH is easy. You can measure it, and you can do a calculation, and you can just add acid to make that pH go down to where you want it to be. But when you're trying to decide, how much acid to add for balance and for flavor, there really isn't a formula for how to do this. And I already mentioned, try to stay away from the recommended target ranges for acidity that's recommended for wine, because they don't always translate well into mead. And the best way is just to calculate your acid addition based on what you determine in tasting trials. So tasting trials, determining how much acid to add. I think tasting trials are one of the most fun parts of mead making. Where everything else is microbiology and biochemistry and calculations. This is really where the art of mead making comes in, because what your palate tells you may be different than what my palate tells you. And it also can depend on what type of acid you're using. I tend to use tartaric acid over others, but there's times when I might make a blend, maybe 50-50 tartaric acid and malic acid, or I might use only malic acid. And the way I decide that is by making tasting trials with the different acids and then deciding which I like best. So doing a tasting trial will help keep you from making the mistake of adding too much acid. You can always add more later if you need it, but if you've made a mistake and you added too much, it's much more difficult to address that. The way I do a tasting trial is I make up a 10% tartaric acid stock solution. You can do the same thing with other acids also. And a 10% solution is basically 10 grams that's been dissolved into a total of 100 milliliters of distilled water. Basically, after you weigh out the tartaric acid, you mix it with 80 milliliters of water and stir well until dissolved, and then you top off, ideally in a volumetric flask or graduated cylinder, up to the 100 milliliter mark. And you can store this in your refrigerator up to a couple of months. It doesn't last forever. I mean, it can get mold on it or something like that. But usually you can store it for up to a couple of months in the fridge. And the reason why I love using a tartaric acid solution that's 10% is the math is very easy. If you pull a 100 milliliter sample of Mead, you add 1 milliliter of your 10% stock solution, that will be raising your titratable acidity by 1.0 grams per liter. And so that's how you can figure out how much of an addition do you need to add. So I recommend performing tasting trials early before palate fatigue sets in, or before you've drank too much and you're not really aware of what you're doing. Keep good records, because you might think, oh yeah, how much I want to add, but then like the next day when it's time to do the acid addition, you might not remember, well, what was it that we decided that we liked best? And I find it's always best to involve others in this process. And the reason for this is there are some people who are blind to certain faults, and some people may have different preferences. So it's nice to have others, and then you can kind of vote on it and see where you think the certain level of acid addition tastes best. So here's how I might design a tasting trial. I always have a sample of the control, which has no acid added. And then I might have, you don't want to do too many of them because you will get palate fatigue. So anywhere from say 2 to 5, once you get up to 6 samples, it gets really hard to distinguish between them. And maybe in this 100 milliliter sample, I might have 1 milliliter, 1.5, 2, 2.5, 3. And the math is very easy because you're using a 100 milliliter solution, adding 10% tartaric acid solution. It's basically telling you how much acidity you'll need to add to your main batch once you determine which one of these is your favorite. There is also a wonderful website called Wine Ads where they will set up your tasting trial for you. It has a lot of other useful calculators at that website, so I encourage you to look Wine Ads up and use that for determining not just your acid additions but also other additions as well. So to conclude, acids in Mead. pH, titratable acidity, and total acidity are all different methods for measuring acidity. They're related, but they're not the same. There are slight differences between them. They're all useful depending on exactly what your reason is for measuring and what you're planning to adjust for. Some of the reasons why we measure and adjust pH and titratable acidity is it helps keep the pH within the desired range so that optimal fermentation will take place. It manages the long-term stability of our mead. It helps keep the molecular sulfite within the desired range of 0.8 milligrams per liter or more. And then acidity also has organoleptic benefits in regards to appearance and flavor. So I think about pH as something that I measure to ensure optimal fermentation and to keep the sulfite level where I want it to be want to help me when I make or determine sulfite additions. And I think of the titratable acidity more as determining how much acid I need to add, if any. So I think of the TA as more of taste, for the taste of the mead and all of that. And even though there are a lot of things online talking about what your acid ranges should be based on the level of sweetness, I strongly encourage you to not do that, but rather determine your acid additions by doing tasting trials. It's fun to do it. You'll be surprised by what tastes best. You may think you don't need to add much or any acid, and you find out that it actually does help a lot. I find that adding acidity can be the difference from having a mead that's just okay to one that's bright and crisp. It seems to even bring out the fruitiness in some of the mellow that wasn't there. It's an illusion, of course. The fruitiness was always there. It's just the acidity improves our perception of that. In another talk, I'll be talking more about falling endpoint phenomenon. Here are my references for acids in mead. Again, as always, I encourage you to look these up for yourself and not take my word for anything. And I will be posting the PDF of handouts of this in a link for you to download at your own convenience. And again, thank you so much for watching. I really hope that you find this video and all of our other videos helpful in your quest to make the best mead possible. Thank you.